forecast. The talk is going to last for around 30 to 35 minutes, following which there'll be an opportunity to ask questions. So if you have any questions, please put them in the Q&A and we'll come to them after the talk. Over to you, Natalie.
Thanks, Isabel, and thank you for the invitation. What I'm going to talk to you about today is kind of like the kind of an overview of what we've been doing at Reading in conjunction with lots of partners over the last decade or so, I suppose, since 2010 when AO erupted. So I'm here speaking today, but lots of this work is led by Helen Dacre at Reading and also many, many more people. I started writing them down, they filled up the whole slide. So apologies if you don't see your name there, but we're very grateful for your collaborations over the last decade or so. Oh, let's see. There we go. So really this work is aimed at volcanic ash forecast for aviation. So quite a lot of my talks are entitled to fly or not to fly. So should your plane fly or have a different route around the ash cloud? So my outline is we're going to talk a bit about why we care about the ash, and then quantifying model uncertainty using one approach, which is using an ensemble. I'll talk a little bit about what one of those is, and how we can reduce that uncertainty. And we've been looking at two different ways of doing that here at Reading. And then finally, maybe the most important thing is how we actually communicate this to the end users. So why are we interested in the ash? Well, in 2010, Europe came to a standstill when AO erupted. All flights were cancelled for quite a number of weeks. It had huge economic implications. People were stranded away from family. It impacted all sorts of different things. Even the World Chess Championship was delayed by a few days, and the Liverpool football team had to get a ferry rather than flying to their Champions League match. So lots of different impacts. And there's quite a lot of people, when you talk to them, they've all got a bit of a story related to this event. Either they were stranded or they know someone else that was stranded. So it's kind of quite a big event that the general public are quite aware of. Fortunately, they don't tend to happen that often. And when it happened, there was quite a lot of media stories saying like how the forecast went very good. The forecast of the ash went very good. And one of the most famous quotes was from Ryanair's chief executive that's basically called for the charts from the imaginary computer generated model need to be done away with. So he wasn't a fan because he wanted to fly his planes. On the back of this eruption, the UK Met Office moved from presenting just charts that were showing the possible the location of the ash to charts that actually showed ash concentration, because this was believed as an important thing to know, because planes could fly through a little bit of ash, but not a lot. So these are the new kind of supplementary charts that are issued by the London VAC at the Met Office. And the colours indicate the concentration of ash. So the cyan colour is what they call low, so between 200 and 2,000 micrograms per cubic metre. The grey, 2,000 to 4,000 micrograms per cubic metre, and then the red, greater than 4,000 micrograms per cubic metre. And then for during AO, the aviation industry and Rolls-Royce engine manufacturers suggested that it was this red area, the greater than 4,000 micrograms per cubic metre, that was really the important areas to avoid. However, these maps look very nice and look like they can be useful. However, all these concentrations are subject to a level of uncertainty to relative areas of the eruption source strength. So basically, they make assumptions about how much ash has come out of the volcano, which obviously has an impact on the ash concentrations. So we've moved from a kind of location to a concentration in these maps. So here's that map again, which again, don't think I said, but that's actually from the 2011 Grimsbottom eruption the year later. When we spoke to the aviation industry about these new kind of supplementary products, we asked them what they might do with them. Where wouldn't they fly? This is at a user workshop. And we gave them this hypothetical ash cloud over the UK. So here the colours mean the same. So the red is the highest concentration, so greater than 4,000 micrograms. And then down to the grey and then to the cyan colour. And we asked them, so this is a room of about 50 different experts. They're working in various parts of the aviation industry and in forecasting. And we asked them to draw where they wouldn't fly their plane. So draw a region where they wouldn't fly. And this is what we found. So the grey is the outline of the red. And the red colours are kind of a heat map of the no-fly zone. So you can see there's a huge range of areas, ranging from about 70% of the original red area to about 1,000% of the red area. So even in industry experts, if they're presented with this forecast, they would do very different things. So this is kind of also motivation for some of the work we're doing later to try and help the end user use this information. Of course, this map on the left is just one realization of the forecast at a particular flight level in the atmosphere at a particular time. So if you're trying to make decisions, you'll have multiple maps at multiple times at multiple flight levels. So another area of research we'll talk about later is trying to combine all this together to give information which is useful to a decision maker. And then more recently, there's been a push towards probabilistic forecasts. So instead of just having location and concentration, they want a probability of exceeding certain thresholds at certain flight levels. So this is what they call quantitative volcanic ash forecasting, implemented by the International Civil Aviation Organization. And this is going to come into practice very soon, the end of 2025. And they've defined 5 different concentration thresholds. So more than what I've shown on the previous slide with those products. And also they need to be provided for every 5,000 feet slices. So more slices in the vertical, out to 24 hours every 3 hours. And this is kind of an example product that they have got in their guidance. I think you probably agree it looks quite similar to the product on the previous page with just a few more colours. But I would imagine that this graphic would also suffer the same interpretation difficulties as that were found in our survey. So that's also, these changes also mean there's more maps because there's more thresholds and more vertical levels and more time that need to be output. So that's a kind of big open question at the moment, how these are going to be used. So I've spoken a bit about why we're interested in kind of the what's happening internationally. And I'm going to move on to quantifying model uncertainty. Well, when I say that, where do these sources of uncertainty come from? So the first source of uncertainty is just not knowing how about the volcano itself. So how much ash has come out, how high it went, what's the ash density, what's the particle size distribution, what's the ash shape. So there's uncertainties in that, which are very uncertain in an emergency response situation. There's uncertainties in the representation of removal processes, so by sedimentation and wet deposition in how that's represented in the model. There's uncertainties in the meteorology, so in the winds, which first order advect the ash round, but also uncertainties in the wet deposition. So the rain will wash the ash out, so the location of that. And then also there's uncertainties that we don't know about, and also with other how the model is designed and configured. So there's quite a few cases where uncertainty can come from. One way of trying to account for this is to run an ensemble. So when you run a forecast, you often start from an analysis or your best possible estimate the state of the atmosphere and your volcano, and you'd run that forward to get a deterministic forecast. So one forecast, like the graphics, supplementary graphics I showed before. But what you could do, and that deterministic forecast kind of lies within a climatology. So if you did it lots of times, it would lie within that. But there's some uncertainty in this analysis time, or on what you know about the volcano and the weather. So you could run it forward, you could change those slightly and run it forward, and then you'd get this kind of green area, which is kind of your forecast uncertainty. So all of these dark green lines are plausible. So you can use them to kind of estimate your uncertainty. So we've done a bit of work on this at Reading. We went through the name model, which is the Met Office dispersion model, which is used by the London Volcanic Ash Advisory Centre. So we identified 18 parameters that related to the source or the internal workings of the model. You can see them here in this table. You probably can't read it, but so the red ones are related to the volcano source, and the blue ones are related to the name internal parameters, things relating to the turbulence and the wet deposition, and things that govern the sedimentation. So, and these all have a minimum and a maximum value that we elicited from experts, which was a long process, but we got there eventually. And then for an example case, so we looked at one day from the AEA 2010 eruption. We varied all these parameters all at once using Latin hyperQ sampling. And for this work, we were working with some statisticians, and actually we ran the model something like 15,000 times. So we had a lot of realizations. And when you look at this, you can get a very wide range of predicted ash fields. So on the left, we kind of have the worst case scenario for this day, which this is the day that had the most ash in it. And then on the right, we have the best, what we call the best case, which had the least ash, so it would have the least impact on aviation. So you can get a very wide range of predicted ash fields given a plausible set of parameters. So what you could do is combine all these, and where you get small differences, you would have high confidence there's ash, and where there's large differences, you have low confidence. So unfortunately, I don't have the next figure for the AEA case, but this is another hypothetical case. So where we've coloured the level of agreement, so where the ensemble members agree to be, so the yellow is less likely, 0 to 10%. The orange is likely, so 10 to 90, and 90 to 100 is the red area. So where almost all the models agree that there will be ash with this greater than this 4 milligram per meter cubed threshold. So you can see even that you get quite a wide range, a wide area that's ash is affected. So we can build these ensembles of simulations. Obviously, in operations, we wouldn't run 15,000 because that would take too long. But there is work down at the Met Office in building these ensembles at the moment for this QVA, the quantitative volcanic ash probabilistic forecasts, which need to be in place very soon. So now I'm just going to move on to looking at ways we might reduce this uncertainty. So you saw it for the AEA case, there was a very, very wide range of ash distributions. So at Reading, over the last few years, we've been looking at kind of two different ways of doing this. First one's called inversion modeling, and the second one is ensemble member filtering by matching to dispersion simulations to satellite observations. So I'm going to talk about the inversion modeling first. Both of these cases, both of these techniques have been applied to the Raikoki 2019 eruption, and this is a volcano which is in the Northwest Pacific, over here, kind of northwest of Japan. This eruption was in June 2019, and it lasted about 12 hours. It had an estimated ash plume height of about 13 kilometers, which means the ash got into the stratosphere, and over 40 aeroplanes were diverted during this eruption, which doesn't sound that many, but it was quite disruptive at the time. When I talk about meteorology and varying the meteorology, we're using the Met Office Global Meteorological Ensemble, MOGREPS-G, which has 18 members and about, it's got a 10-kilometer horizontal resolution. I'm a meteorologist by training, so all my talks have a weather map in them. So Raikoki is here, and at the time of the eruption, there was a cyclone set out here to the west, which we might see an influence of that in a minute. So what do I mean by inversion modelling? Well, the inversion modelling system that we use here at Reading is the INTEM, which was developed at the Met Office, originally deterministic, and it takes in an a priori emission profile, so a kind of a first guess of what the emissions from the volcano were, combines that with satellite observations and dispersion modelling to give a best estimate of the emission profile. So I quite like pictures rather than words, so we could change those boxes into pictures. So here we've got our first guess here, and some satellite information, some a name simulation, and it goes through the inversion system to get out this time across the bottom and height up the side profile of the ash that's released from the volcano, constrained by the satellite observations. This technique takes into account uncertainties from the satellite and the dispersion model, and we can use either just ashy observations or ash and clear sky observations in the system. And the vertical resolution is about 4 kilometers, and the temporal resolution is 3 hours in the standard form, but you can change that. Another thing that we've done, because I've been talking about ensembles, is to change it so we can run this inversion system with an ensemble of meteorology, so the MOGREPS-G, and instead of getting one constrained profile, we can get a set of 18 with using this meteorology. So for the Raikoki case, this is a plot of the ensemble member along the bottom. So these have all have plausible meteorology in them, and the total fine ash emissions at the side, because obviously for aviation we're interested in the ash that remains in the atmosphere for a long time, which is the hazard to the airlines. So there is a range of total ash estimates for about 0.32 to 0.71 teragrams, which is a lot less than the 11 teragrams, which was calculated using your first guess or a priori estimate, and the mean is about 0.5 teragrams. And this spread represents the variability within the ensemble meteorology. It's always good to have a bit of a sanity check. So different estimates from the literature also are similar values to what we found here. So they've got different total amounts of ash. How different do they look in the vertical? So this is a bit of a game of spot the difference. We've got all the different members here. They are similar to each other, but there are differences when you look. So, and remember, this is a log scale. So some of this member here has got more yellow down here. What's interesting to note is that they all kind of removed, I think this might be on the next slide actually, if we take the prior emissions here and compare it to the mean of the ones on the previous slide, it's really noted that actually ash that was emitted near the surface in the first 4 kilometers is removed by this inversion process, as well as it being greatly reduced. All the cases that we've looked at, so Grimm's, Votten, and the AYA 2010 eruption, they all reduce the amount of ash that from the prior, although that is not constrained by the inversion system. If the observation suggested there was more ash, it could add ash. What was also, we could look look at is where the ash is emitted. So we said that in the prior there was a lot emitted near the surface, which is these purple bar here, and the bright blue is in the troposphere. So and then the light blue is the stratosphere. So the ash, there's much more fractionally, there's much more ash emitted in the stratosphere for this case. Why is that important? Well, it's very hard to remove ash from the stratosphere. There's no raining clouds up there, so it's very hard to deposit the ash out, and often the winds there in the vertical, that they change quite a lot with height, so you get this vertical wind shear which really spreads out the ash further. This is similar to what was found in another paper where they were looking at SO2 from Raikoki. So we're fairly confident that this is the case. So this slide's got quite a lot of figures on, sorry. This panel B for this time at midday on the 22nd of June is the mean of all the Ensemble members for the best guess emissions. Below that is column loading from one satellite algorithm, the ORAC algorithm, and C is from the Met Office algorithm applied to the same satellite. So these are both from the same satellite with different processing algorithms. And panel A is the Ensemble mean from this Ensemble where it's been through the inversion system. So you can see that the reduced emissions has led to this much reduced ash distribution, although you can see it is in the same very much the same location. If you then look along this cross section with the dashed line, our reduced emissions are this blue line compared to the satellite retrievals, which are the black dots and the red crosses. So you can see for this time along this cross section, it matches very well. And the first guess is shown in this cyan color. You see that's quite far away from some of these the satellite observations. If you move forward in time, 24 hours, the panels are for the same thing, and we can see this the first guess, this prior emissions. You can see the ash is now getting wrapped up around that cyclone that I mentioned before, and you can see it's kind of bifurcating here. Again, when you look at the mean for the posterior, so the ones that have been through the inversion system, the ash is in the same location, but the magnitude is greatly reduced. For this time, although it still is probably a better fit than the first guess, the cyan, it doesn't match as well to the satellite observations, especially when you look at this part here. Where's my here? So this branch here, it matches much better in the northern branch and the southern branch. So I've just spoken a little bit about the inversion modelling. So we've extended the kind of standard approach to include meteorological uncertainty, which gives us a bit of confidence in this inverted source term. And I haven't said, but this technique is suitable for long eruptions, so it can be run iteratively, kind of again and again, to include more and more satellite observations to get the best match that we can. So now I'm going to talk a little bit about Ensemble member filtering by matching dispersion simulations to the satellite observation. So the inversion modeling kind of does that, but this is a very much more explicit way of doing it. And also this time we constrain the source parameters and dispersion model parameters, where the inversion modeling just looks at the source. This is a bit of a kind of a flow diagram of how this works. So we make our ensemble like we did before. We do the Latin hypercube sampling. In this case, we run 1,000 members. Again, varying all of the parameters at once. And then we compare it to satellite observations. And for this, it's easier to look at the kind of pictures. So at top left, we've got the satellite detected ash cloud and one of the simulated ash clouds, and then we match where the pixels, they have pixels in the same place. And then we calculate something that's called a hit rate. That's not really important for you to know, but it's about the location of the ash. And then we calculate something else called the percentage difference. So looking at the magnitudes, and then if they're within a certain tolerance of for both of those things, we call it the limits of acceptability. Then we keep that member and its parameters, and then use those members that reach those limits to then form the distribution of the next run, and iterate that forwards every 6 hours. So you can see here that the green arrows show you an example member where the hit rate was accepted, where it wasn't, it was rejected on the left. And then further down, one where the percentage difference is accepted, but the red is rejected. So with each of these steps, we run 1,000 members, and there's 10 parameters that are perturbed. And yeah, we keep the members that match, and then use those parameter values to sample from for the next lot of 1,000 members. So this is quite computationally expensive. You wouldn't really want to be doing it for an eruption that lasted too long. But Raikoki's fine. It's kind of short pulse eruption. So it seems to work quite well. So we did this. Well, I say we. This work was led by Anto Caponi up at Lancaster. This was his COVID project. And he ran this 8 for 8 iterations, and you can see in the figure that distributions start in these purple bars, and as you run it forwards, they get more and more peaks, so they kind of converge towards parameter values. So these gave us mean plume height of about 11 kilometers, and a mean density of about 2,000 kilograms per meter cubed, a mean distal fine ash fraction, so how much ash that was the fraction of ash that was emitted that's available for long range transport was about 10%, and mean total emissions of about 0.5 teragram, which is what we, similar to what we found with our inversion modelling using INTEM. So I've just given you a bit of a whistle-stop tour of the Ensemble member filtering, and it's quite computationally intensive and really only suitable for pulse eruptions, but does give results which are comparative to the inversion modelling. The last thing I was going to talk about was communicating this model uncertainty. So we've done a lot of work in quantifying and trying to reduce it, but then still how we're going to communicate this to the end users. So we've talked about kind of how to visualize likelihood or where things agree. But obviously we've got these threshold boundaries, we've got likely, less likely, very likely boundaries, we've got time, we've got height. So you can get quite a lot of maps. So even if you're just thinking about 5 concentration thresholds like here, you've got 5 charts. So you kind of have to try and manage that. And they've got different likelihoods. And so how can we really condense this information for the decision makers? People are actually going to have to decide whether a plane flies or not. So the way we approach this at Reading is to use a risk-based approach. Quite a lot of you will be familiar with weather warnings that are issued by the Met Office. They look a bit like this. So we've got a warning matrix. So along the bottom, we've got impact, and up the side, we've got the likelihood. And they often come with kind of what to expect and what you should do. So instead of thinking about the wind or the rain, or whether I should put my garden furniture in my shed, we've come up with similar things for ash and aviation. So if it's in this yellow region, it's kind of like low warnings. Maybe you would still schedule your route, but you would check your updated forecasts. If you're in amber, you might load more fuel, check updated forecasts, and then when you land, perform some engine checks to check the engines are still fine. And if it's red in this high risk region, then you might consider alternative routes or cancelling. So this work was led by Andy Prater here at Reading, and they looked at a hypothetical eruption of Katla. And in this case, they used 600 members with the same kind of sampling technique to produce the simulations as what we've done before in the other work. And so you can get maps like this. They were interested in the route from JFK to Heathrow. And you can see this is based on ash concentration. And you can have on your map where your flight would be and whether you would fly or not. So this is concentration. You could also do it for dosage. So this is where you're looking at the integrated amount of ash along a flight path, which engine manufacturers might argue is more important than the local concentration. You can also look at this in the vertical along a flight track. This is what's on the bottom panel, so you can see whether in the vertical where the ash risk is. We've also been looking at, rather than just having maps of where the ash is, just projecting that onto the actual flight track. So here in panel A, the flight track is coloured based on the ash dosage risk. And then in panel B, it takes the maximum of the ash concentration risk and the ash dosage risk. So there are some slight differences here. So you can see we've got a bit of orange here, which comes from the concentration. And then again, on the bottom, along the trajectory, the blue is this dosage, and the pinky colours are the instantaneous concentration. So this is there is kind of a demonstration project of this tool available on the web. It's not quite in operations, but we think it'd be quite cool to be able to move your plane and it'd be coloured in by the risk of encountering ash or any other kind of meteorological risk. Going back to Raikoki, the 2019, so it's the same case. We can see we've done something similar. Here the colours are slightly different. So we go from green for the low risk to this dark blue for the high risk. And if we use our kind of best guess of the emissions, then we get this bottom panel. So there's quite a large region of blue, dark blue, this high risk. Whereas if we use our inversion system, actually the forecasted risk area in total is reduced by about 35%, and the high risk area is reduced by almost a half. So this could have quite a lot of impact on aviation operations. And you can see here, this is a flight track from this day, possible flight track from this day, and it would be impacted, especially the southern one, by this ash cloud. So you can see this is an example of a real world case where this approach the risk-based and inversion approach might be useful to decision makers. We've also gone a little bit further and you use some decision theory, which is a statistical technique which takes into account operational losses. So we take our kind of likelihoods and convolve them with a loss table. This subject's a whole talk in itself, but we also applied this approach to Raikoki. We're using Anto's 1,000-member ensemble, and you can just get very different risk areas. We can see here on the right. So the top panel is if you just use your most likely, so the likelihoods. The middle panel is if you've got high costs for engine maintenance compared to flight cancellation. And the bottom panel is if it's equal. So if your engine maintenance compared to flight cancellation is the same, then you get this region of very, very large region of very, very high risk. So you probably wouldn't want to fly your plane anywhere in the Pacific if that was the case, but you might make a different decision if you, as a business, the cost for engine maintenance were bigger than flight cancellation. This work's published in BAMS, so you can take a look if that's something that you're interested in. So this risk-based approach hopefully condenses lots of information. They both say the same. One of them's meant to say fast and one's meant to say robust, sorry. So hopefully it can help make fast and robust decisions. So it's based on the best science that we have. We're trying to make this step forward to this route-based, flight-based perspective where you can look at multiple routes on the same space, and you can actually extend it to incorporate financial losses using decision theory. So that's something else we've been working on. So that has been, sorry, a bit of a whistle-stop tour of what we've been doing at Reading over the last decade or so. To summarize, we've got deterministic forecasts can have large errors in regions of large horizontal. So basically the meteorology can incorporate errors, and also inaccurate volcano source parameters. Ensemble forecasts can represent the uncertainty, but can result in information overload and a very large range in concentrations and dosages. And we've been looking at techniques that can constrain these ensembles, mostly using satellite information. And risk can be used to communicate uncertainty and hopefully make fast and robust decisions. And with that, I'll leave it there. Thank you.
Thank you very much, Natalie. That was a really interesting talk. We now have time for questions. So if you do have any questions, please put them in the Q&A. I can see we've already got a comment in the Q&A at the moment, which is from Charles Forrester, who says that their company specializes in flight data and have a lot of safety contacts and would be happy to help if that's of interest. So that's Charles Forrester, Aerobytes. So it might be interesting to you.
Yes, that would be great. Quite a lot of these things are commercially sensitive, so people aren't always happy to share. So no, it'd be great. Especially we're trying for the decision theory work, we're definitely trying to get like some numbers about how much things cost, and that also was quite tricky. Yeah,
that does sound really useful. I have a couple of questions to start us off. First being, you said that these models are very computationally expensive. How long do they take to run?
Okay, so when I say computationally expensive, not computationally expensive compared to a climate model that you want to run for thousands of years. But to give some context, in the Volcanic Ash Advisory Centre, they have to be able to produce a forecast within 7 minutes. So typically the runs that Anto was doing to get the 1,000 members through using the computing power on Jasmine, which some of you might be familiar with, that was taking about a day to get the 1,000 members through. But yeah, the forecasts which the operations centre do are very, very quick. So they're about they'd be about 7 minutes on their big supercomputer.
Okay. And your talk is largely focused on ash. Can this be extended to SO2, which I see is now a question which has come up as well?
Thanks, Kat. So before COVID, there was a big assessment at the Met Office about extending this to SO2. I think COVID kind of made that all go a bit quiet, but definitely the inversion system INTEM was originally written for not for volcanic ash at all, but for kind of other sources of different kind of trace gases in the atmosphere. So it definitely could be adapted for SO2. And I think there is someone at the Met Office that does actually have a system that does work for SO2. I think SO2 forecasting, definitely is in the future. I mean, from a safety point of view, the Rolls-Royce aren't as concerned about it from an engine damage point of view. I don't think. Maybe I'm wrong, I'm not sure. And also, but it's not very nice if you're in the cabin and with lots of SO2. So there are kind of health impacts that way.
Yeah. Okay, so our next question is from Ibrahim. Did you take ash composition into consideration during your design and run of the forecast models? And if not, why?
No, we don't take ash composition explicitly into the design, but they do in the ensembles. We do change the density, which is related to the composition, and there is an ability now. Not that we haven't done it, but there is ability to change the shape of the ash in the forecast as well. Why don't we do it? It's because there isn't actually a lot of real-time information about what it should be. So, and the study that we did where we did the 15,000 member ensemble, it actually found that changing the density didn't change the answer all that much compared to some of the other parameters, like the height of the ash or how much ash came out of the volcano.
Okay. I now have a question from Charles asking, saying you mentioned particle shape in the introduction. What difference does that make?
I'm no expert in this, but it's basically it'll fall faster or slower depending on the shape.
Yeah. So I have another question, which is, well, I thought it was really great how you did sort of a focus group to look at how people interpret the forecast. Have you done something similar with your newer forecasts and
No,
how people might interpret that?
No, but we think that is a really important thing that we somewhat, well, I don't know whether us, but someone should be doing, because very soon that they'll be issuing probabilistic forecast information as routine. So it would be I think it would be very eye-opening to know what the industry is actually going to do with that information. It's a bit of a change for everything in aviation. So it's not just forecasts of volcanic ash that are going to go probabilistic, it's also for other met phenomenon. So convection, icing, turbulence, all of those things are going to be given as a probabilistic product. So I think there's probably a big bit of work there to try and understand how people are going to use this information.
Yeah, I think that would be really interesting to see and very, very important.
I think we were quite,
Yeah.
when we did that focus group, we were quite surprised actually about people's what they kind of wrote down in their survey, and also the discussion, how that they weren't really convinced about uncertainty. They thought it just meant you didn't know the answer, and that they would just look for someone that would tell them like where the ash was or wasn't, rather than actually taking the uncertainty into their decision making.
Yeah, that will be really, yeah, it's a really important thing to consider. Yeah, very interesting. So I think we can end the Q&A there. So thank you very much, Natalie. And before we stop the webinar today, I wanted to mention that we don't actually have any webinars planned for the next few months. We're trying to get speakers at the moment, so everyone should keep an eye open for announcements by email or by social media. And in the meantime, you can access many of our previous COMET webinars on YouTube. So thank you again, Natalie, for the really interesting presentation, and for everyone for joining and listening today. Thanks very much. Bye.
Thanks. Bye.